Hello, everybody. I am very happy that I can welcome you on the next yet another lecture of our course. Today it will be a bit experimental because some of the materials which I'll be covering today is completely new. So we will see how it goes. Hopefully there won't be too much errors in the slides, but if you are watching the recording, it may be possible that some things have already been fixed in the slides on the course website. So if you think something weird is happening, you can look there. I, of course, hope that it doesn't happen, but the best thing how to estimate this is from past experience, and the past experience says that there will be errors. There are always errors, even if I try. So before I will start myself, are there any questions on your side, something you would like to know? Nope. Yes?
I use WQ network instead of online. Then I want to copy the weights anytime.
So you want to copy it anytime, or?
So if I use WQ network, then the argument of update frequency goes away, right?
No. Do you want? Yeah, you don't want to, but you have to take one. So in the double deep Q networks, I will open it here. What we do is we choose or select the action in a different way, right? So in the usual deep Q network, we choose the action by looking at the target network and also using the target network to compute the estimates. So with a double deep Q network, we choose the online network, the current one, to select the action, and then we evaluate it in the target network, but we still need to update the target network once in a while, because they train the same thing in both approaches. They just train the current parameters, the online network. They only differ in how they estimate the return. So you still need to decide where you will copy it, because the only thing we just changed is this one. Because like in the usual double Q learning, we actually had these two Q1 and Q2, right? But in this double deep thing, we don't actually have Q1 and Q2. The only difference is that we actually use the fact that we have the online network and the target network.
So there is no even 50-50 switching.
Yeah, no. No, we don't really do the switching. The only difference is that because the maximization bias problem was caused by the fact that when we did the estimation of a state, right, we looked up the action which seemed the best, and then we took the value of that action which seemed the best. And this was optimistic because if it was there an error, we erroneously said that the state was too optimistic. So now we use two networks, and we do this decision, this estimate of this state in two steps. First, we select the optimum action, and we do that according to the online network. So one of these actions seems to have the best estimated return. So we take it. But then the value of that, we compute it using the different network, using the target network. So it can happen that the action looked nice for the online network, but for the target network, it's like meh. So, and this is how we can get rid of the bias, because we choose the best action and then evaluate it using two networks. In the old algorithm, which we had on lecture, 2 or 3? I will try 3. Right, it's somewhere after V of policy, I think. Then we So here we really had two of them and decided which we train. But the important part is this one, where we choose the action according to one and then evaluate it using the second. And so in the deep Q network, they said, okay, it's even fine if we just use the target network and the online network for it, which is cheaper than having two of these differently. And also, if you got rid of the target network and you would be updating both of them, then it would probably not work, because the goal of the target network is to stabilize the training so that there are no short feedback loops which could cause the divergence. Like when we talked about the divergence, the problematic part was if we could train and that would cause the error to actually grow. And we could have done that, so a short cycle could have caused the divergence. With the target network fixed for 1,000 steps or something, means that all our feedback loops have a length of at least 1,000 or something. But if we had just Q1 and Q2 and we would use them immediately, switch them in this way, I could imagine that it could have diverged quickly because the feedback loop can still be short. Yeah, so the question is how to combine double Q learning and n-step method. So I haven't really seen any paper about it or something, but I guess using tree backup algorithm, where during the estimation phase you would randomly sample one of those Qs, probably could help. But this is nothing what I would read in a paper or something, right? But if I were to use tree backup with the double Q learning, then here we choose the action and here we compute its value. So I could imagine, because this pi, this is most likely a greedy policy with respect to some estimate. So I could imagine that you could define this using Q1, and then you could use Q2 to actually do the estimation. So this is the place where you would have two different things, where you would unentangle the action selection and then the evaluation. So this is something what I would try, but when you look at it from the usual n-step kind of thing, well, if you have expected SARSA kind of like n-step SARSA like that, then this is the part where the double thing would be used again, the action is chosen according to Q1 and estimated using Q2. That should also work, but the explicit important sampling ratios would be complicated. So I don't have the answer ready. But one would have to think where it can be done. There are definitely many possibilities, and I haven't seen any of them in the paper which would show that it's better or worse or something. In the rainbow, which we will talk about later, they do this kind of expected SARSA or Q-learning kind of thing with 3 steps, and they do the correction only in the last estimation. They don't deal with the reward, they just have 3 of them summed together. They just ignore the important sampling ratio, hoping that it will be fine. And it is actually. So we discussed the deep Q network at the end of the previous lecture, right? And then we started talking about rainbow, which included these various improvements. So we already discussed the double deep Q learning. Then we discussed the prioritized replay, right, which sampled the actions not uniformly from the buffer, but according to the TD error. And the idea is that well, for the transitions where the TD error is large, the loss will be large, the gradient will be large, so we will learn something. And finally, we talked about the dual-link networks where we modeled the distribution as like a single advantage for the state plus the advantages, so the differences of the values of an action minus the average. I have still the old slides here. They have been slightly updated on this front, so maybe I can go there just for fun. Right, so we consider like a value which will be just an average of all the action value functions, and then the advantage would really tell me, okay, on average, how this action is better or worse compared to the average output in that state. So these are the three ones which we have seen, and now we can discuss three more, right? Because there were 6 in Rainbow. So the first one will be just a single slide, cherry on the top. So the authors say, okay, n-step learning seems fine. So let's use n-step Q-learning so that the estimate of an episode is, well, the 3 explicit rewards plus gamma to 3 times our estimate from the next state. So here it's without the double deep Q-learning, but when we combine it together, it will be double deep Q-learning. The thing is, when you do this, the algorithm actually has been changed because it's not off policy anymore, right? Because these rewards, they depend on the actions which we took with some behavior policy, and because this happened, because if this is in the replay buffer just, it happened with probably a different policy, so we should deal with it, in theory, but the authors just don't. They don't even say that that is happening, they just say, yeah, we will just do it, and hopefully it will be fine, and it is in practice. But they really don't say whether they did some evaluations. Although maybe they use n just 3, because the larger the n, the higher of policy correction probably should happen, right? So maybe for 3 it's just small enough that it's not a problem. Yep, so that's what they do. Now, things will start to get more interesting. So both the 2 improvements which I want to describe, they somehow want or try to estimate not just a single value, right? When we have an action value function, we usually think about the expectation, right? About the mean. But the thing is, we have a whole distribution of returns, and being able to see the full distribution might actually help us. Instead of just a single point estimate, seeing the full range, randomness, or something could be interesting. So in the noisy networks, they do it by a very weird approach, and that's, we will have neural networks where their parameters, so the weights and biases, will be perturbed by some noise whenever we run a computation. Right? So instead of the usual weights, we will say, okay, every weight will have some mean, then some variance, standard deviation specifically, and whenever we want to do something with the parameter, we will generate random noise, right, and sample. So what we do here is the parameters are no longer constants, but they are distributions, right, which we model by a mean and standard deviation. So if we have a fully connected layer, right, normally that would be a weight matrix plus a bias. Then what we will do is the weight matrix will be represented as a matrix with the means and then the metrics with variances. And then during computation, we will really like sample from this distribution, right? And then the same thing for bias. So this way, the neural network will generate a whole distribution of returns. Like normally, we run the network and we get one number. So now, if we run the network with the same inputs 20 times, it will generate 20 different numbers because different noises were used for the parameters. So it's like an implicit way of generating distributions. It's like a weird way. I haven't actually seen it afterwards, but it's kind of interesting to see that things like that can actually be useful. So that's what the noise nets do. Now these means are initialized as usual because they are like the normal parameters. And we also have the standard deviations, so they are initialized to like have this 1 over square root of n, where n is the number of the input neurons, so that the variance of the output will not change much, right? If you remember how the Glorot initialization works, and then that's the reason why the square root is there. And then we have some hyperparameter. Well, in all the publications which I have seen, this is 0.5, so just small numbers. So one technical point, generating random numbers is hard. It takes some time, especially if you want a whole matrix of the random numbers, right? This is like a huge number. So even if you generate on GPU, it would be quite slow. So just as a technical improvement, what the authors do is they generate the whole matrix using low rank approximation. So they just do a vector of noises for rows, vector of noises for columns, right? And then they do an outer product of these noises. And then they generate the whole matrix, just as a speed up, right? Because they can generate just, I don't know, n plus m random numbers, and then they quickly generate n times n matrix, while generating n times m random numbers would be just too costly, right? One has to be careful so that the properties or the statistics of the noise will be the same. So what we will do is, because we will multiply the noises, we will compute the square root of it before, because then it means that after multiplying two of them, we will get a similar distribution as if we didn't do it. And they generate the noise samples for every batch, but every example in the batch share the same noise. Again, just a technical thing. Generating too many noises would be too costly, and it's actually fine for each batch to share the noise. So when we apply this to the deep Q network or double deep Q network, the thing is, we will no longer use epsilon greedy strategy. Instead, all the fully connected layers will be noisy networks, which means that on different runs, the outputs will change. So we will just use greedy actions, but if two actions have similar estimates, then probably sometimes one will be better, the other times the other will be better, right? Because they will like switch there. So the exploration happens not with epsilon greedy action selection, but with the noise which we put into the network, which generates the distributions of the returns. And so if two actions are close enough to each other, then some of them will be like they will change places or change turns, being the most the one with the largest estimate. Yes. Yeah, so the question is, why do we want the random weights? So yes, I think that this, like what we want is we somehow would like to faithfully represent the stochasticity. If in some environments, some actions like when we have our estimates, then either they are correct, and like a greedy action might be vastly better than all other ones. But sometimes, even if the greedy action is larger by some non-trivial amount, it might be the case that it's not really great. It's just like kind of noise. So what we want ultimately is to be able to represent policies in a better way. Because right now our policy is greedy with respect to our estimates, but for some environments this might be stochastic in the sense that it doesn't really matter which action we choose because they have very little influence on the outcomes. Sometimes it might be the case where one of the actions is much better and the other are significantly worse. So being able to somehow represent this nicely would allow us to sample better among others. So from this point of view, yes, like this is the main output of that, but we don't just want to replace epsilon greedy sampling per se. We want to have a better idea of what a good policy is. So if we see the whole distribution of rewards, then if for action A1, you know that the distribution looks like this, and for A2 it looks like this, then it's obvious that A2 is better. So even during exploration, we might not want to use A1 too much. But if the distribution looks like this, then even if there is the same difference between the means, then we probably want to sample A1 as well a lot, because there is a good chance that it will actually produce a good outcome. Yep. So let's have a look at how well this does. So what we will do is we will compare to the usual deep Q network and also the dueling deep Q network. And there are the graphs showing the median scores of the games. So you can see that at the beginning of the training, the difference is not very large, but using the noisy nets allows you to get consistently better in the later stages of the training. So it might be interesting to see how random or the predictions actually are. So here, what we can see is how the last layer looks like after training. So after the last layer, for some of the environments, the size of the average noise parameter is kind of small. So sometimes the model might decide to generate quite deterministic results. For some of the environments, it nevertheless generates, even after full training, it still says that the results are stochastic. So it seems to be somehow able to model the stochasticity of the environment. And when we look at the penultimate layer, so the one but last layer, then there the model really considers stochasticity for many environments. But the fact is that I don't think people understand this well enough. I think it was an attempt to do it. Okay, let's somehow deal with the stochasticity and being able to represent policies better, but it's kind of weird. And we will not see it later, but at some point it seemed to do something interesting, so that's why we are talking about it. So,
do we also train the variance parameter?
Yes. We train both. So with the noisy nets, we have 2 as many parameters in the fully connected layers, and we train both the mean and the variance. The network might decide to, or the training might decide that it doesn't want the output to be stochastic, in a sense that these standard deviations could go to zero. And that's what these graphs actually show, because these graphs, they show you how large this variance parameter is on average. So for some of the environments, especially for breakout, it is decided to generate deterministic outputs. But for some of them, it never decreased these variances to zero because it was useful to model the output distribution.
And also, when we choose when we verify square root of n, is that like just the input neurons to the whole network, not just the one layer?
It's the input neurons to this one layer. This is like a standard trick in a sense that when you have a neural network, a layer, sorry, when you have a layer and you want to initialize the weights here, then what you want is you would like to keep the variances in a sense that if here you have got some variance of the data, then you want to initialize in a way that the neurons here will keep the variance. And because these neurons are sum of n elements, which are always the input times the corresponding weight matrix, then after you do the math, you will want the Wi to have a variance of 1 over n, because you sum n of them together. So when you do some of these two together, then the result would have a variance, which would be the average variance of the individual xi's. So this is just to make sure that at the beginning of the training, the output will roughly keep the variance of the input. So it won't explode nor vanish. And we initialize, like these things are initialized with the square root of 6 over n plus m. Right, uniform from -1 to plus this, right? Because again, we want the variance to be 1 over n. So this is like 2 times 3, right? This thing is just an average of n and m because we want the same property to hold also in the backward path. And this 3 here is because when you have a distribution uniform from -a to a, then its variance is a square, it's a square divided by 3. Yep. Yeah, that can be computed. It's not very difficult. You just compute the integral and everything. So when you want this variance to be 1 over n, right? Then this a, when you look at it, will be the square root of 3 over n. Right, so that's how this square root and 3 get there. But this is like I would say, usual kind of initialization. Because if this was to like 20 times so much, the activations would grow very large, and then the network would not train, because neural networks expect the output variance to be reasonable. Because that's what all our loss functions expect, and if it's not, we would need to use different learning regs than the usual ones. I'm now thinking whether they had this experiment in the paper. So the question is, like, during the inference, right, whether the noise should still be used. So my guess is that they don't do it, that they use it as an exploration again. So they use it during training to see whether, like if they have these two actions, whether it makes sense to also consider an action which has smaller average, but has a reasonable chance of getting better results. But I think that in the end, during the inference, they go for the greedy with zero noise. So now let's get to the sixth improvement, and that's the most beefy in a sense that by itself, out of these six improvements, it gives the highest improvement, I think. We will see the graphs later. And this is like the extension of the noisy nets idea. So instead of modeling this expected return as a single number, right, let's model the whole distribution of the expected returns, right? So this is the value distribution. Formally, it should be action value distribution, but in the paper they just say the value distribution, so I say it as well, and they denote it with Z instead of Q, because the Q is by design an expectation, right? So here the Z is actually the distribution, right? So it's not one number, it's a whole distribution which says this reward has this, this return has this probability, this return has this probability, right? So the Z here, it has got returns, and here it tells you how likely it is to obtain them, and Q is this just with one number, and the Z is the whole shape. Right? With the noisy nets, we had a way of sampling from this distribution, kinda, right? Because the different noises meant that we sampled from, like, ideally this distribution. It wasn't done explicitly, it could have done whatever, but this is what we hoped the noisy network generated, like samples from this distribution. Now we will represent it explicitly. The good thing is that even for distributions, much of the theory works as before. So we can define a Bellman operator, right, where the Bellman operator for the given Q will do like one step of the of the environment, or like one step of the simulation in the environment. So we say, okay, so after doing one step, how the result will look like? Well, we will get the one-step rewards. That again is the distribution of possible rewards for that state and action, right? And then gamma times the value distribution in the next state and the next action, where the action is sampled from the policy. We could also have the optimal operator, where we would choose the action to be the one maximizing things, right? Because this is what we did for the normal temporal difference kind of thing, right? We had this Bellman backup operator. We have proven that it is contraction. So we knew that there was this unique optimum value function, right? So this is the analog of that, and they even prove that, again, this is actually a contraction under a suitable metric. That suitable metric is some like reasonable version of the Wasserstein metric, and this thing is a contraction there. So repeated application of that converges to some fixed point, and if that is reached, the Bellman equality is reached. So hopefully this will converge to the optimum solution. If the policy is fixed, it will actually converge, but we like do this generalized policy iteration, right, where we like improve the policy, do its evaluation. So we never know whether this will converge. We just know that if it would converge, it would be optimal, but we have no guarantee that it would. But we are in the same settings as we were before. So I need to do like small reminder, because we'll be seeing this Wasserstein metric a bit for today's lecture. So like here is a formal definition, but instead let's have a look at what this means, right? So the Wasserstein metric allows us to compute the distance between two distributions. So we have mostly been using KL divergence for that, for example, on deep learning, right? When we have two distributions, we can say how different they are by looking at their KL divergence. The Wasserstein metric is first a real metric compared to the KL, which is not. And it has some better properties which will be useful for us. But what it does is that if we have two distributions, then what we want to do is we would like to find the so-called optimal transport, right? So you can imagine that we have got these two distributions, one and then maybe the other. And the Wasserstein metric, what it does is it considers like a plan how the elements will be transferred, moved between these two distributions, so that this transport starts with the first distribution, and after the transport, we would get the second distribution. And this length, like the transport itself, right, so the distance which each element has to travel between the original position and then its transformation, is the smallest, right? So it's like an optimal transport in a sense that we will find the transportation plan. So formally that's a coupling, but you can really think about it as a map which tells you, okay, this element, move it into that element, so that the length which we need to travel for this transport plan is the smallest, right? This will be like enough intuition for us in the general sense, but we will talk about the one-dimensional case a lot. So in one-dimensional case, the optimal transport has an analytic solution. So if we are in 1D, right, then let's have two distributions. So let's have a distribution with a cumulative density function. Like the cumulative density function tells you the probability of an element or anything less, right? All the cumulative density functions start at 0 and at 1, and they are monotonic. So, and this tells you the distribution at hand. Normally, we work with PDFs, density functions, and that are the derivatives of that, right? The density tells you how much density you have at that point, which is the derivative of the cumulative density function. So imagine that we have got two of them, F and G, right? So what the optimum transport does is that, well, when you have this element which have some specific cumulative density function, then you want to move it horizontally in this graph, right? Because you knew that, okay, so here is where 30% of elements are. So after the move, you want this element to be here, right? Because now the 30% of elements need to happen at this point. There is no much choice in how the transfer should look like. It has to be like that to actually just make the distributions the same, right? So the Wasserstein distance in this case is just an integral where we will consider all these probabilities, right? And for all the probabilities, we will look at the distances between these 2 points. Right? So what we need to do is we need to take the probability. We need to use the CDF to tell you at which element we achieve that probability. And then the distance here, that's the transport which we need to do. Like formally, it probably looks terrible, right? Because we need to say f minus 1, f2, like inversion of f, because cumulative density function, you give it an element, and it gives you a probability, like how many elements are this or smaller. When we do the inversion, then that's a quantile function. Like we give it a quantile, 30%, and it gives us an element so that 30% of the elements are this or smaller. Right, so that's why the minus 2 to minus 1 here. So we have got these two quantile functions, and we consider quantiles from 0 to 1, and we just look at the distances between the corresponding quantiles. So this is danger sum, so it's just so that you don't feel bad. If you are overwhelmed now, don't feel bad. So, how are we going to do it? How are we going to represent the distributions? Well, what the authors proposed is to do like a comb, like a regularly spaced so-called atoms, right? So if you imagine you want to generate a distribution, I don't know, between 0 and 5, right? Then we could generate some fixed number of locations. Yes, a question? Thanks. So the question is whether here I'm not missing the minus ones. So in the 1D case, this is actually the same because you can do like variable substitution in the 1D case. So you can actually say, okay, now let's call this Q some specific value. Like the thing is, here we integrate over the quantiles, and here we integrate over the elements. So it's not missing. It only works for one Wasserstein distance, and it only works for the 1D case. But this is actually equivalent. I wrote it there when I started writing the slides. We will never use it anywhere, so it probably would be better for me to drop it because it's not really interesting to us, but it's just a different way of how we will compute the integral, right? So what we will do is, in this one integral, we go over here, and then we measure these distances. In the second case, we go here, and we measure these distances. But in all cases, we compute this area. And maybe that's also a nice way of looking at it. I maybe should have told you, like, when you have these two CDFs, then the Wasserstein distance is just the area between these two curves. I haven't realized it until today, which I should probably have, but that's what it is. So it was useful to keep it there anyway, and it would be nice to have one image which would draw this nicely. Thanks, I've learned something new. So, assume that we have the distribution, that we have a distribution we want to represent, and let's say that we will know a range of values which we will care about, right? So this is 0, 5 for some example, so let's say I've got some minimum and some maximum value. Discrete distributions are nice, so what we will do is we will say, okay, we will divide this range from Vmin to Vmax uniformly, and we will represent this distribution by considering like a discrete support, right? So it's like this. Probably like this. Well, maybe this goes even there and there. So what we will do is we will represent the distribution by the probabilities of these individual atoms, right? Well, they are like, for all the elements which correspond to that atom, we will know how large this volume is. So what we will have is, for n atoms, we will just have n numbers which will tell us the probabilities of these like bucketized, discretized portion of the range. Right? We will want these probabilities to be Fourier distribution, so we will want them to sum to 1. So here, the zi's are the coordinates of these centers or of these supported values. So we start here on the Vmin, and we use this increment of z, so that here we will have the last one of the z's will be the Vmax. And so when we model this, then until now, for a given state and action, we generated a number. So now, for a state and action, we will generate a distribution with n elements, which will be the probabilities of these fixed locations, fixed supports in our distribution, right? So the network will generate some Fi, the I means ith atom, so the probability will be just the softmax applied to the logits generated by the neural network. And that's for state and action, right? So that's what's new. Right now, our output has one more dimension, n numbers, which are probabilities in specific fixed places. So what we want to do is we want to do this one-step Bellman update, right? So during training, like normally we say QSA is is the RSA plus gamma times QS, like this, right? We have the one-step update, the temporal difference one-step estimate, and we say, okay, our Q value should be closer to this estimate, right? So we have a mean square error between our original value, our estimate, and we hope that once this converges, once there is an equality there, we will arrive at the solution which we want. So here, we want to do the same thing, but on the distribution front, right? So we have a distribution generated by this Bellman update, and we want to say, okay, our original distribution, ZSA, should look more like that. The tricky part is that when we compress the distribution by Q, right, when we apply the discounting, then the support of the distribution changes, right? So we have got the distribution Z. Then we do the scaling, right? So the scaling makes the reward smaller, so it will make the distribution narrower. And then we add the reward, which is just a shift. But after this, these atoms, these like rectangles, they have a different support than the original distribution. So we need to map it back to our atoms, right? So after doing this multiplication and this addition, we end up with a distribution where the comp is somewhere else. So we need to do the mapping. So they have the so-called projection, that's the phi here, which looks terrible on the first side, but it will be fine. Don't worry, right? So what happens is that we have these places where we want to compute the probabilities, and now we can have a value which looks like this, for example, right? So here we know the probability for that, and we need to represent it using the these two ones, right? So what we will do is we will represent, we will really split it here, right? And then we will say, okay, so some part will go here and the other part will go there. So we will do linear interpolation and divide this probability into the two neighboring atoms in the original distribution. So it looks terribly, but what we say is that for atom I, right, what we want to do? Well, we want to consider, so the I, that's the orange one, right? I. So we will consider all j's. So the j's are the bars in the transformed distribution. We will take their probability, right? Pj, that's the probability, that's the blue probability, and we will distribute it to the z's, to the original supports. And here we measure how much the blue j atom should correspond to the ith atom in the orange distribution. And what we do here, well, we look at the coordinate of the jth. Oh, I should have done it in blue, right? So how this zj transformed? It was multiplied by gamma and moved by r. So this zj is like the middle of this distribution. We clip it to the Vmin and Vmax because we cannot represent values outside of this range. And then we look at the difference between that and the zi, right? So we measure the distance between this and this, right? This part. And if this is less than 100%, then we will get something. The orange zi will get a portion of the blue one, and the portion will be exactly this like percentage of how far this center of J actually is from I. And on the other side, the difference will be the remaining part, right? So when we have this one J, some of them will go to the left, some of them will go to the right, and we will like take the whole volume and distribute it to those two neighboring things. Now this seems weird in a sense that they do the full sum of all the j's, but when you have one zi, there are only two zj's which would give you non-zero element, right? But they just implement it like that. So this might seem weird, but geometrically, we have just squashed things and moved, so we just like linearly put them or give their probability to the original support. So great, we can do this Bellman update and get the distribution in the original format. So now what we want to do is we want to make the value distribution ZSA to be more similar to this one-step update. So how we want to do that? Well, we have two distributions. We want them to be more similar. Ideally, we would minimize the Wasserstein distance between them, because that's the metric for this operator is a contraction. But at that point of writing this paper, the authors didn't know how to do it. They even proved that an SGD algorithm cannot do it, the usual one. So instead, they say, okay, just let's ignore the Wasserstein metric and then just minimize the usual KL divergence, right? We know how to do that. It will make them closer. All our proofs are now not working. It doesn't matter that this operator is a contraction in the one Wasserstein metric. If we are minimizing KL divergence, well, but whatever. The proof doesn't mean much anyway. And they did it, and it was working, right? So what we do is we minimize the distance between the thing which are training, the action, the value distribution, and then this one-step update, right? So we have this R plus gamma times the target Z, right? Because we have a target network. And we need to choose an action. So where to get an action, normally we just take the action which maximizes the expected return. So we will do the same thing, right? So we will consider all possible actions and compute the expectation of the estimates. Like these estimates, the Z theta bar, that's a distribution, but with a fixed set of probabilities, so we can compute the expectation really just by computing really the average, or by computing it explicitly. So that will give us an action, and that we use as an action in the next step. So it's like a Q-learning, right? It's just that we need to explicitly choose the action and then evaluate it in 2 steps. We normally do this in the double Q-learning, like choose an action and then evaluate it. Here, we need to do it like that. We need to write it like that because the choosing considers an expectation, but the evaluation gives you a full distribution. So this is probably terrible. And then there's this projection, right, which will copy the things back to the original support. Don't worry about it if it seems weird. It is weird. There is a loss. The loss function is implemented here explicitly so that we can see it's not so bad, right? So we have the network which computes the probabilities of the individual atoms. So that are the Pi's and Pj's, right? So when we have the state and action, we can compute the QSA, either the Q itself, like it's an expectation, or the Z, and we represent it by these ZI's, right? The probability, we represent it by these PI's, the probability of an atom ZI. So the expectation, if we want to compute it, is really just a sum over of Pi Zi, right? Because Zi is the return that one value, and the Pi is the probability of actually generating that. So what we do here, well, we will compute the our expectations, like expected return in the next state and all actions, and we will do an argmax over that, right? So that gives us the action which we want to follow. So here that was the A star, right? And now we need to compute the loss. So we need to evaluate the KL divergence. So the KL divergence will inside generally compute the sum of Pj. So I just want to use the same notation, so it will be okay. So after the projection, this will have probabilities of mi, so there will be mi times the logarithm of pi. So that's generally what's happening here, right? We just need to compute the probabilities of the atoms of these unwieldy things on the left side, right? And in order to do that, what we do is we will go through the support in this distribution, right? So these are the J's. And what we will do is we will copy the probabilities into L and U, where the L and U is like lower and upper. It's like the two orange distributions, like there are two orange atoms in the underlying distribution. Like so, the J is still the blue one, and we explicitly compute PL and PU, which are these two values. And we just use the linear, I'm missing a word, how it's called? Linear transformation to really distribute the probabilities. So, the algorithm itself, it's usually called C51 in the papers. And the 51, that's the number of atoms which we will use, right? So every estimate for a given state and action will be represented as 51 numbers. and the Vmin and the Vmax will be minus 10, from minus 10 to 10. So we will be able to nicely represent things here. Outside of this range, we will just glue it to the boundary values. This only works because we are using this reward clipping, right? So all the positive rewards are internally clipped to +1 and the negatives to -1, and we have this gamma as the discount factor. So there is a good chance that we will fit inside this range. Even if you can see in the papers, you can get 98,000 of points in this environment. Our estimates will mostly stay in this range because we have clipped them so that they are there. So compared to all the improvements which we have seen, which means the deep, double, dueling, prioritized, and prioritized dueling architecture, just using the distributional one gives you better mean, better median, and generally it's just much better. But when you act, you still use epsilon greedy, right? It's still like, okay, we just do the estimates, we have the full distributions, but when you choose an action, we are always doing the epsilon greedy kind of approach. So, there is an example of how that might look like, how the estimates looks like. So here is the Space Invaders game. We have a ship on the bottom. You can go to the left and the right, and you can shoot. So here, what this shows is that, and now I have to think. So there is a non-trivial chance that some negative return will be obtained, and there is also a chance that some positive ones will be there. Generally, you can see that the distributions between the left, right, and do nothing doesn't really change much. So it shows that it doesn't really matter much what we do. We just have not to fire. Because if we fire now, we will miss, and then we'll be killed by the alien, which is not very visible. So that's why all the laser actions are here at 0, while all move actions or not doing anything are more on the right. It's funny how these distributions look nice in the sense that they are like Gaussian kind of like. The authors say that they don't think it's like that maybe it's caused by this projection step, which makes everything very smooth, right? When you have a distribution because of these linear interpolations, then they think this is what happens, and that's generally how the distributions look like. So it can model nicely things which are like bimodal. So it can see that there is not just one maximum, right? But it can really see, okay, either we can lose or it can it could be better. So all these things can be modeled nicely, and also the like the fact whether we are sure about what will happen, right? Or whether there is a large uncertainty of whether like what the outcome will actually be. Yes?
So that C51 was just a simple network with
Exactly. C51 is just DQN with this for loss. Yes. No prioritized things or anything. So here, this result means it's just by itself improves on many of the combinations. And when we evaluate it together with the other improvements, it will give us a lot.
Do you know what those two columns on the right side?
Yep. So this means better than human baseline. So this is how many games is this better than the humans, and this is better than DQN in the number of games. So this means in 50 out of 57 games, this gets you a better result. So it's just another way how you can evaluate. That's later on when we will be seeing thousands of mean scores, then people instead look at this like as another metric, like in how many games are we actually better. So here is the ablation experiment considering the number of the atoms, right, which we use for the modeling, and the deep QN baseline. So in some of the environments, like in Pong, it doesn't really matter because, well, even the DQN itself works well. For the other ones, generally, the larger number of returns, the better. So the red one seems to be on top. And there are some cases where the 51 atoms are actually needed for the training to happen. Maybe even more would work even better, but that would use more resources or something. So probably it would be better to use even more. They just didn't. The 51, the weird number is because if you go from -10 to 10, right, then with 51, the middle one will be 0, one of the atoms, and then it will be like nicely distributed around. That's why they use all even, no, odd numbers. So now, let's connect everything together, right? So in Rainbow, we will do all these 6 things which we have just seen. So we will be doing n-step updates. We will train by minimizing the KL divergence between the current distribution and the projected n-step update, n-step estimated value distribution. So the n-step is just here and in this discounting, right? We use the prioritized replay. So the prioritized replay samples according to our TD error. So in our case, the TD errors will be proportional to the KL divergences of these 2 distributions, right? And the network utilizes the dueling architecture. So for each logit, it computes like a value function and the advantage function for it, right? So each logit is computed from 2 quantities, the one which works as an average for all the actions, and then the advantage one, the one which is specific for the actions. We also need to make sure that the advantages are real advantages, so we subtract we center the advantages which we have there. Now, it looks terrible, but it's just, until now, it's just a straightforward composition of whatever we have seen, right? Yes? Sorry, no, the n step here is that when we compute the estimate of the state, we will do n steps in the environment, and then we compute the value estimate of the state where we got after these 3 steps. So the idea is, if you are have this star shape and you want to fire, then 1 step means that we will just do 1 tick in the environment, and then we will estimate the value function here by doing this 1 step, so obtaining 1 reward, plus computing our estimate on this step using the target network. So for the 3-step algorithm, what happens is that we simulate 3 steps, right? And then we say, okay, our estimate of this state action value is this 1 reward, 2nd reward, 3rd reward, discounted proportionally. So that's this part, right? And then we compute our estimate So we look at our action value function in this state 3 steps in the future. So that's this part where we do the discounting to gamma to n, and here we consider the state as t plus n. So that's the same thing as n-step SARSA, for example, which we did on previous week. So the idea is that the estimate which we get is contains more immediate rewards, so it should be more accurate. Like in the Monte Carlo, this n would be infinity, right? So we would unroll the episode until the end, and then we would say that the sum of the discounted rewards would be our estimate, right? In the temporal difference, we do just some fixed number of unrolling, and then we say, okay, and then the remaining of the episode, I will just estimate. Luckily, I am always computing the estimate, so I have them, so I just take the action value function in that state and look at it. And we use the target action value function for it, right? Because that's what we do in the DQN itself, so that's why there is a bar there. Although it's the double version, right? So when we choose the action, then this is the online network. So I know that this is terrible, but like if you look at it just by itself, but it's really just a composition of all it's meant to look weird, right? Menacing. It's really just a composition of all the steps which we have done because, well, they have been chosen such that they can be combined together in the first place. We use the noisy networks, so all the linear layers are replaced by the noisy equivalents, and that's it. So let's have a look at some hyperparameters. We use no exploration, right? Because the noisy networks will deal with that for us. We initialize them somehow. The target network period is still there, so we copy the online network to the target network every 32,000 steps. We have a very small learning rate. We use the priority sampling, prioritized replay buffer. We use the exponent 0.5. That's this part, right? We take things proportionally to the TD errors, but we don't want to overdo it. So we say, okay, square root, that's somewhere in the middle of the 0 and then to 1. We do the correction, like in the prioritized, in the prioritization or in the prioritized sampling, we correct the fact that we are now sampling differently, and we do the same thing what they did in the original paper. So we start with some minor correction, and then we let the correction to be larger and larger, and at the end of the training, it is clearly like a full correction. We use these 3-step returns and 51 items representing ranges from -10 to 10. Mm-hmm. Yes, it's meant as exactly as at the end of the training. So let me revisit the prioritized replay. So we have the priority, which is the TD error to omega, and then exactly we need to do this sampling. Okay, I didn't tell you. Okay, maybe I haven't said it, so I'm sorry. So they do this even in the original paper. So they start with beta of the 0.4, which means that this correction is not full. It's just we just do it slightly. We don't care too much at the beginning, and larger beta makes the variance larger. So it's like let's start just slightly, and exactly after these 200 million frames, we want to end up at end 1.0, and we just use a linear schedule of increasing the betas. Thank you very much. So let's have a look at the results. So here are the DQNs, then all the all the 5 improvements and some other algorithm which we'll ignore for the time being. So don't mind the yellow one. It's not a very good one in the first place, and we will talk about it on the maybe next lecture. All the improvements, so all the colors are there, and then this is rainbow, right? So combining all of these improvements together really makes the results considerably better. So the improvements are orthogonal in a sense that stacking them up makes the performance even better. So looking at these, the orange ones are the distributional network, so that's C51, right? So the C51 is better than all the others. That's consistent in what we have just seen. There, close, we have the dual-link architecture, that's the green one, prioritized replay, right? Double deep Q networks. The noisy networks don't get much, right? But combining all together seems great. Now, this graph is like the inverse of the other one. So here, we have a full rainbow, and then we subtract one of these 6 improvements to see how worse it would be if we haven't used that, right? So when we have it, then the worst thing would be to stop doing the priority sampling, right? If we had everything but the priority sampling, the results would be worse, because the effectivity of training would suffer, because many of the transitions we can predict nicely, and so we just lose, spending time on them without changing the model, right? Surprisingly, there is the multi-step here. So not doing the 3-step thing would also be very bad. They haven't evaluated just using 3-step sampling at all. And then we have the distributional stuff, right? So not doing the distributional stuff would also be bad. Now, this is quite a surprising, right? Because if instead of the 6 things you'd use 5 of them, this nice composition would not happen, right? You would just roughly be on the same places on the left graph. So only using all of these, at least these 3 ones, then was actually needed. On the other hand, when you look at the violet one, that's the double learning. So at this point, the double learning as per itself doesn't give you much, even if just using that was kind of low. And similarly, the dual-link architecture gives you nearly nothing at this point, in a sense that it has been subsumed by the other improvements, right? So if you needed to drop something, you can drop the dual-link and you can drop the double probably, and it would be kind of good. But not the other ones. The other ones are still important. Woohoo! Yeah, more graphs. So, questions? So if there are no questions, let's have a break, and then we will return back with more interesting ideas. So let's now see what people have done to improve upon what we have discussed so far, and what we will talk about now is how to make the distributional approach better, right? That's mostly what we will do. So we will try to improve C51 by an algorithm which would be, I don't know, either better working or more sane or whatever. So in the C51, what the authors have proven that the distribution Bellman operator, right? So the thing which we denote this T pi, and that's this one step, right? So when we have the value distribution, then if we do this one step, so R plus gamma times our estimate in the next state. So this operator is a contraction with respect to the Wasserstein metric, but they didn't know how to do it, right? So instead, after performing this step, we needed to do the projection, right? So that this probability was divided into two neighboring atoms, right? And then we tried to minimize the KL divergence between these things, these two distributions, without being actually able to prove or show that it works. Later, actually, the same team of authors came up with another idea which actually manages to minimize the Wasserstein distance, or the one Wasserstein distance, which is, well, for a theoretically pleasing, right? Because we have an algorithm for which we have some kind of guarantee, and although it will deliver better results. So how to do that? So the main idea is to represent the distributions in a different way. So in C51, what happens is that when we have the network, right, it gets S, then it produces an output where for each action A, we generate some number of atoms, right? And these are, for each action, probabilities for specific returns, right? So this number is the probability of the return being minus 10 or less. This number is the return being minus 90.75 or something like that. So this is what we do there. So instead of this, we will represent it in some like a transposed way, and we will consider not fixed locations, but we will consider fixed quantiles. What we will do is we will say, okay, so let's, instead of saying this value minus 9.75 has the probability of 0.01, like we will say, okay, the return for which the cumulative density function gives you 5% is this specific number. So here the probabilities will be fixed uniformly. So what we will do is we will say, okay, so if we'll do 100 of them, it will be like 1%, 2%, 3%, 4%, until 100%. And for each of these probabilities, we will predict quantile, so a value where this or something smaller has a probability of 1. Right? So when we look at the distribution, like previously, we had these fixed locations and their probabilities. Now we will look at the cumulative density function, and what we will do is we will consider fixed probabilities, and we will predict the returns where these probabilities will be attained in the cumulative density function. So there should be an image here. Yeah, right. So for these fixed probabilities, we will say, okay, so this probability is achieved at this point, this one, at this point, this probability, at this point, this probability, at this point. So our predictions are these 4 quantities, 4 numbers, right? They are quantiles, right? So the quantile is like the value of the return where the cumulative density function gives you some specific probability. Yeah. So formally, we can describe it as saying that the cumulative density function is just a step function, right? And at every quantile, like at every return, the probability will jump up by 1 over n, right? So we will always represent the distribution as this staircase, and we describe, we say at these places the stairs are. This can be also described as the distribution, not as the quantile, but as the distribution itself. Like if we consider a Dirac, it's like this event with like probability of 1, which is like infinitely narrow, like this non-existent kind of thing. Then you can think about it as like one impulse, like an impulse with probability of 1. So we can imagine that we have got these impulses in the quantiles, right? And then we average them. So this is just a weird description of saying, well, the derivative of the CDF is infinite there, but the Dirac is exactly the thing which have this infinite value. So it's weird, and we will not use it, so I'm just thinking that we could do it, but it's probably better to look at it from the cumulative density function point of view. So that's the main difference, right? That's why it's called quantile regression, because we will think about the quantiles. By the way, there is an image somewhere near the end, so I will cheat and go here, right? So here, the C51, right, generates these distributions for a fixed range of returns, right? Here, what we are just describing, we will generate the values which have these given probabilities. So we'll have an idea of where the probabilities lie. But because we are predicting the returns, we are no longer forced to use fixed range, for example, of return, right? We can now model anything, not just from -10 to 10, but whatever we like. So now I need to go somewhere back. Yep. So what do we get from using this different representation, this quantile distribution? So we no longer need a fixed support, so we don't need the given range. We can model anything. This weird projection step where we modeled, where we like transformed this updated atoms back to the original one is no longer needed. We can just multiply the quantiles, and that will make the distribution narrower. Ooh. Right? And this parametrization will actually allow us to minimize not the KL divergence, but really the one Wasserstein metric. So we know that it would actually converge if we did at least a policy evaluation, right? So all wins. So the one Wasserstein distance just tells us, as I was taught a moment ago, the integral, or the area between the two CDFs. So it looks weird, but that's what we need to do. So now, imagine that we have whatever distribution Z. It doesn't need to be a cumulative one, right? Like whatever distribution. And we want to represent it using a quantile distribution, right? So this is sometimes called a projection operator, in a sense that we have an arbitrary distribution and we want to find a quantile distribution which approximates it the best. So you can imagine that we have got the space of all the quantized distributions. Then we have this one Z, which doesn't have to be a quantile distribution, and we need to find the orthogonal projection there. So such a quantile distribution which minimizes the one Wasserstein distance. The good thing is that in this 1D case, we know how the solution actually looks like, right? So formally, this quantity, how we can rewrite it, well, the quantile distribution is very specific in a sense that it is these step kind of distribution. So what we can do is we can compute this area under the curve for each of these independently, right? And then we will always know what the quantile of the quantile distribution is, right? So we will consider all these n steps. And for each step, we will integrate from the previous probability to the current one. And here are the quantiles of the distribution which we want to project, to find. And the other quantile, well, that's just the quantile, right? Because the z theta is just a collections of theta I, each for a probability tau I. And this has actually an explicit solution, right? So if we want to minimize this, I won't be showing you the proof, but if you are interested, there is a reference for it, right? But the quantile distribution is actually kind of intuitive, right? So when we want to compute the quantile for tau 1, what we will do is we will compute such a value that the original distribution has a quantile of like the middle one in there, right? So how does this work? Is that when we compute the errors, we know that Yep. So there is a mistake, right, in this image, because this part should have also been read. So what we do is we know that we need to find a quantile for this tau 1, and the question is what value to choose. And the thing is, what we end up with is to choose such a value where exactly the other distribution would have this midpoint quantile in the middle. So here, this Z2 is chosen such that the original distribution passes just here in the middle of these two probabilities, and this holds for all the cases. It kind of makes sense, right? I can go to the left or to the right. Always I am paying for these two areas. One of them will get larger, the other will get bigger when I move around. And choosing the one where I'll be just in the middle seems kind of intuitive. I have not really read through the proof, so I cannot show you anything better, right? But we want the quantiles so that they correspond to the quantile midpoints of the original distribution. And generally, in the paper, they show that composing these two things together is a contraction. This is just for formal completeness, right? So when we do this one-step update, what we do is we do the Bellman update, so one step, that generates a generic distribution, not necessarily a quantile distribution, something, right? And we project it back to the quantile distribution. So if we do these steps, they are a gamma contraction in a suitable metric, so repeated application of that is fine, right? So if we do the one step and the projection, and the projection will be achieved by doing one step of an SGD, so not full, but a step in the direction, then we have some kind of guarantee of how this will work. So what we need to do is we need to find a way how to estimate quantiles, right? So imagine that somebody tells us, okay, we have a collection of samples from some random variable, and we want to estimate 10% quantile. So the value which, if you sorted the samples, would be in the 10% of the sorted elements, right? If we can do that, then we will say, okay, so we will set this theta 1 so that it is this quantile of the distribution Z. So now assume that we have just a distribution P with some samples. So right now, no reinforcement learning, nothing. Very simple settings. We have a distribution and we have samples from it. What is usually not, or what I don't talk about it, for example, on the deep learning course or anywhere, is that optimizing different losses would actually produce like a different interesting values. So let's say that I have got a lot of samples X, right? And I will try to generate one outcome, one value, and I will do it by minimize the mean square error between the samples and the value which I want to minimize. And if we do that, if you really minimize this, then the estimate is actually the mean of the distribution, right? We don't explicitly talk about it when we talk about MSE, but MSE is specific in a sense that if there is some stochasticity, so in the neural networks, if for the same X you could have gotten multiple outputs, then the mean square error would converge to the expectation. But surprisingly, the other losses don't do that. So if we would use another one, you wouldn't estimate the mean, but something else. Right? This is a nice general fact, which I didn't know 2 days ago, maybe 10 days ago. So how to see that this is true? Well, as usual, what we will do is we will look at what the like minimum looked like. So we will compute the derivative of the loss with respect to our estimate, right? So how does this derivative look like? Well, the expectation considers just X, not the estimate, so it just stays. Here we have 2 times the term times the derivative of this term itself, and it's just 1 because this X hat gives 1 and nothing else. And so what this means is that we can generate 2 expectations. The first is the expectation of X hat. Well, that's just X hat, right? Because it doesn't depend on X, so we can take it out. It's fine. You know, I always say at the beginning that the teachers say the linearity of the expectation is so great, so here we use everything, right? We split it into 2 elements and then take one value out. And the second part, this one, right, that's just the expectation, that's just the mean. So now, if you have put this into the other side and drop 2, you would get that the estimate is actually the mean. It's great. Oh, I like it so much. So now, let's think about what would happen if instead we minimized the absolute difference, right? So the mean absolute error. Mean absolute error is just the absolute difference between these 2 quantities. It's something which you don't see much when you train a neural network. But if we did it, what would happen? Well, the resulting estimate would actually be a median, right? So it would be a 50% quantile. So why is this? So first, why this works intuitively, right? So let's say that we have got some samples. So if you have your current idea of the result. So if you sample a value which is smaller, right, then the derivative of the loss will be a constant, and it will say go towards that value. And this length of the step, right, it will not depend on the distance. It will be the same distance for all the small values. The same thing if the samples would be larger. So if the axis would be larger, the loss would say, okay, increase. But again, this value of the increase would not depend on the distance. So if it not depend on the distance, it depends only on the ordering of the elements, right? So this will want to be in the place so that half of the elements are above and half of the elements are below, because at that point the strength which pulls you up and which pulls you down are equal, right? Because if you are too low, right, if you would be too low, then the strength which pulls you up would be larger because there is larger number of elements above you. So this will be this will be the in equilibrium for like when we are in the middle. So this is how the proof looks, or what the proof does, right? But the intuition is perfectly fine. For the proof, we will need to use the Leibniz integral rule. So we will need to compute the derivative of the integral where the quantity which we are computing the derivative of is actually one of the bounds as well. That can be done. Generally, I am just, let's say that all the functions are nice enough so that this can be applied. I actually haven't seen any paper mentioning what that actually is. Even on Wikipedia or in the papers, the people just do the differentiation of the integral and then just hope that everything is fine. So I'm going to be as lazy as they are, and I will just say, well, this only holds when the functions are nice, whatever that means. Actually, in the Leibniz theorem, the infinities cannot be there. There are cases with the infinities where this even doesn't work. But for this specific case, it can be over like sidestepped somehow. So I will not dwell into it that much. Generally, it seems that it could be true. So how does it look like? So this expectation is like the integral I have to do now with the probability and then the value which we care about. So because it's the absolute value, what we will do is we will separate it into two cases. The one where the x is smaller than x hat, right? In that case, this quantity is larger or equal to 0, so we can get rid of the absolute value and just keep the parenthesis there, right? And that's why we are integrating only from minus infinity to x hat, because only for x's which are x hat and smaller. And then the upper part, in the upper part, this inside is smaller than 0, so I will swap the sign to make it positive, so to deal with the absolute value manually. So now we will actually do the derivative. So the derivative of that generally has three components. The one is the case where this could increase or decrease, right? The other term is when this would increase or decrease. And the third one is what happens with the inside, right? Because we are computing an definite integral, and things change. So these bounds can change, and the density can change. So there would be three terms, but in our cases, neither of these bounds make any difference because, well, changing minus infinity, like this doesn't depend on x, so it doesn't change. This part depends on x hat, but the density is 0 at that point. So moving the bound slightly has no effect because the density at that point is 0. So we can ignore that. So the only thing what happens is that we need to compute the derivative of the inside of the integral. right? And in order to do that, well, the only interesting x hat is this one, so I will just keep px there. In the second integral, again, this is not interesting because it doesn't depend on x hat. Changing this doesn't change the result because this is 0 at that point. So again, we will compute the derivative of this, and that would be minus px. So now, what we will do is we will say, okay, so this thing, that's 1 minus the integral from minus infinity to x hat, right? Because this is the cumulative density function, so the full integral is 1. So if we have got one part, we can do the other and say 1 minus, right? The good thing is that then these two things will be the same, so I have got 2 times the integral from minus infinity to x hat, and this 1. And so what does this mean? This is an integral of the probability density from minus infinity to x hat. Well, that's exactly the value of the cumulative density function. The cumulative density function is the integral of the density anyway. So that's what we have there. And we say that this is minus 1. So now when we set this to 0, we get that x hat should be such one where the cumulative density function will get you 0.5, which means that the x hat is the quantile for 50%. Yep. So what I want to, this is definitely bad. So what I want to say actually is I want to find such an x star which would minimize this loss. So this is how it should have looked like. Thank you. It will be there everywhere. I will fix it. But what I want to do is I want to find such a value which minimizes this loss, but I should have had 2 names. One is like the candidate value, and then the optimum one. Sorry about that. Which means that some of these should be x hat and the others should be x star, and I will make sure that they are correct. Sorry about it. I don't want you to repeat these proofs at the exam or something. I just want to give you an idea of why these things are true. And they were new for me, so I wanted to be convinced how it works, or that this is really the case. So don't worry about the very complex formulas. The main intuition of saying, okay, the equilibrium means when the strength pulling me higher and lower are the same. Well, that's exactly what this does. So now we will actually get to the quantile regression part. So the quantile regression will actually allow us to estimate a quantile, again, here should be a minimum over z, for a given probability, right? Because when we can estimate the median, which is 50% quantile, maybe we can change the loss so that we will be able also to estimate a 25% quantile or 1% quantile. And it actually can be done. And again, let's do it intuitively, right? We have samples, and we would like to find a place where 10% of the samples are below us and 90% of the samples are above us. So if you imagine the equilibrium, then what needs to happen is that the samples below you have much larger strength than the samples above you, right? So if the samples below you have a strength of, 90%, and these have a strength of 10%, whatever these percentages are, then there will be an equilibrium, right? Because there is 9 times less samples, but they have 9 times more strength to pull you, compared to the upper part where there is 9 times more examples, but each pulling you with strength which is just 1/9. So this is where the equilibrium will happen. So what we will do is we will define a loss. The loss will be asymmetrical in a sense that overestimation and the underestimation will have different weights. So what this loss does, inverts, is that overestimation errors are penalized with weight tau, and underestimation errors are penalized with 1 minus tau. And this asymmetry means that when the loss is minimized, we will have value so that the number of samples larger and smaller will be 1 minus tau and tau, which means that this will be a good estimate of the quantile tau. I haven't seen that before this paper, and I think it's really interesting. So the loss, when you do the computation, can be written like this. This is probably easier, right? So we will consider the mean absolute error, but we will multiply it by this weight, right? And we want it to be either tau or 1 minus tau, so we use the Iverson brackets, and if the x is larger than x hat, then this is 1 minus tau. Otherwise, it is minus tau, and the absolute values will make sure that it is tau. Right? So it's like the mean absolute error with an additional weight. And we can get rid of these two absolute values by rearranging them nicely, right? Because we will make sure that either both of these parentheses are larger than 0 or both are smaller than 0. That means that when multiplying them, the sign will always be non-negative, right? So this part, it's negative when when x is smaller than x hat. So if x is smaller than x hat, then this is 0. So this is also negative, so the result will be positive. And if we go for the other case, it will also work out. So if x hat is if x is larger than x hat, then this is positive. And that means that this is 1. So this is 1 minus tau. This is also, well, I should say non-negative. And we are fine. So we will see that, if we have the minimization here, then the minimizer is the tau quantile, right? We will do it by using the same proof as before, actually. Exactly as what we had there with one more weight there. So we have this loss which we want to minimize. So again, we will separate it into two cases, right? The one which goes for the x's which are bounded by x hat. Then this is positive, so the weight should be 1 minus tau, so we put the 1 minus tau here. And in this case, this is actually negative, so we put the minus here to make it positive. And we have a tau there. Then we will take, we will just compute the derivative of that. So this derivative, again, will just act on the inside. So here, we will have a derivative of -1. So that will change the signs here. So we have tau minus 1. And when this goes here, again, it will be -1. So it will cancel out with this minus, and we will get plus. So now we have these two integrals. So if you consider the tau part, it's like tau part this integral and tau part this integral, but these two can be composed into integral from -1 to 1, so that's the sum of the whole probability distribution, so it's just 1, so it's just tau. And then we have this -1 for this part, and that's just the quantile, that's just the CDF for the given x hat, so the probability of x being smaller or equal to that. And from this, we get exactly that the x hat is the tau quantile of the distribution. So, now this was just an intermezzo showing us how we can estimate not just means, but mediums and general quantiles, and that's what we want in our setting, right? In our setting, we want to represent the distribution as n quantiles, each for probability tau I. And when we have a generic distribution z, right, and we want to represent it by the closest possible quantile distribution, we know that we want to find the midpoint quantiles, so the values which in the original distribution would be the tau hat I quantile. Right, that's this part, right, where we wanted to find these theta i's so that they are such, or these quantiles of the underlying distribution. So now we can do it, right? We can really just minimize this loss. Yeah, we called it raw tau. They do it in the paper, so I use it here as well. So we could minimize this loss. We need to do it for each of the quantile which we have, but we could really just put into the neural network and it would do something. It actually does something. But anyway, the absolute value losses are not very common in neural networks, and one of the problems is that around zero, the loss is not smooth in a sense that it always says go larger, even if we are near the minimum, so it will jump over the minimum a lot. So what we could do is we could make the loss smoother around zero, right? So what we will do is instead of having the absolute value loss, right, this one, which have the derivatives of minus ones, plus ones, we will use the Huber loss. Right, the Huber loss is nice, smooth around zero, right? And then it is linear. So when you look at the derivatives, it's like this, this, and this, right? Nice and smooth. So we will do that, and we can combine our loss, which is just an absolute value loss, and say, okay, so if we are very close, then instead of the absolute difference, we will consider a square. And if we are large enough, we will just use the absolute difference. And we need to deal with the fact that we have moved down a bit, right? So that's this part. It will still be asymmetrical, so the errors above and below zero will be weighted differently. The authors don't tell you or don't speak about whether this actually converges to the correct value, and I don't know whether we still actually get the quantiles or we would really get something else slightly. I don't know. Hopefully not. Probably, well, I don't know. So, how this transforms into a neural network algorithm for reinforcement learning. So the authors call it DRDQN, distributed return DQN, I don't know. K, the kappa here, they either use 0 or 1, right? And 0 means no Huber loss, so just the mean absolute difference, just the quantile regression. And then they use 1, and 1 means Huber loss with the, like around 1, and then the mean absolute error. So what we do is, for a given state, we, again, have a matrix of predictions. Here is the number of actions. and here is n. But compared to C51, these n's are not probabilities of the discrete support, but they are the quantiles. So they tell you what returns have the cumulative density of the uniformly distributed probabilities. So how does the loss look like? Well, we need to compute this one-step update, right? So the one-step update is return plus gamma times our estimate in next state, and such an action which minimizes or maximizes argmax the estimate there, right? So whatever action which gives us the most. So assume that we have got this one transition. So state, action, reward, next state, done, right? It's the same thing as SDQN. So first, we need to choose which action is the one which maximizes the expected return in the next state. So we compute the mean of our distribution, right? Because if we look at the state as prime, right, then we will get the quantiles, right? So we will just compute an average of them, right? Because if you have got a 5% quantile, 10% quantile, 15, 20, and so on, then if you do the average of those, it should give you the expectation, right? That's because we have said that our distribution is just this average of the n Diracs, right? So from this point of view, we can compute the expectation by averaging the Diracs themselves. So this weird QJs are just uniform. They, for some reason, just have it there. So this will give us the expectation of the distribution which we have. We do an argmax, right? So the A star will be the action which maximizes. This must be a mistake. This should have been X as prime. This is directly from the paper, but they don't have it correctly, obviously. So now, when we have it, what we need to do is we need to represent this distribution R plus gamma times Z in the state S prime and A star action. So this is a whole distribution. So what we do is we represent the quantiles of this distribution. We know the quantiles of the Z itself. That's what the network gives us. And it is actually enough just to multiply the quantiles by gamma and add the rewards, right? So the quantiles of the transformed distributions are really computed nicely from the original quantiles. And now, what we will do is we want to compute or minimize this quantile regression loss. So this quantile regression loss, we need to consider all the probabilities, so all the, like we have got this n and quantile, so each of them, we will think about it, and we will say, okay, so this quantile, we want this to be this tau hat I quantile of this distribution, right? Which we, again, represent using a set of quantiles. So what we do is we will compute the expectation, right? And the expectation means that we will just consider all the samples from the distribution, and we will sample the quantiles directly. And that's a good sample. Like if you have this quantile distribution, right, which has this CDF, and you want to sample from it, then you can sample these quantiles, and that's exactly like behaves like a sample from this distribution, right? Because each of those points have a probability which is uniform, right? Because that's what we said. We said this corresponds to a distribution which has the density where each of these points has a probability of 1 over n. So sampling each once is a good sample from this distribution, right? So to consider this Z as a full distribution, we just consider all its quantiles. Right? So we will immediately think about all the values above or below me. So the pool for every quantile will go either up or down depending on how the transform distribution looks like. Yep, so this is some illustration that on a stochastic environment, minimizing these quantile regression kind of approach is better than just estimating the TD errors because, well, the stochasticity is difficult to handle with the usual temporal difference. And this is like a windy environment where there is a probability of 0.1 where you will do a random movement. And if that happens, you need to return and start down here because there is a strong wind blowing up. So there are like multimodal distributions that either it will go fine or you will be randomly thrown away and then you need to go down. So the distribution of the returns is kind of weird, right? So they show on a toy example that it works, and then they train the whole network. So they say they take DQN, and they just change the loss to the algorithm here, right? So all the talk for this. Other than that, it's really DQN. So what we can do is we can compare it. Well, the most interesting thing is the violet one. So that's C51. This is C51. And then these two things above it are the quantile regression. The red one is with the absolute difference. And the, gray one, that's the one with the Huber quantile loss, right? So this seems to work better than the C51. This is the same table which we saw. So mean, median, is better. Number of games which it surpasses the human baseline or the DQN is actually better. The change is in the end not very large. This is one of the things which takes hours to think through on the paper, and then you change this loss slightly, right? Instead of computing the KL divergence of something where the softmax would be, we just computed this Huber quantile loss of these numbers slightly differently. And then it works greatly. So I need to end, but I will finish quickly. The same authors, even later, came up with the ultimate idea, which generalizes the previous approach only slightly, right? So what they came up with is the implicit quantile regression. So the idea is that instead of the distribution generating lot of quantiles, a fixed number of them, let's create a network, right? And the network, it will get S, but it will also get tau, right? So instead of generating a whole matrix of things, let's come up with a parametrized function which will be able to compute whatever quantile you choose. So on the input you say, okay, give me the 3% quantile for this state. So instead of generating a matrix for all possible probabilities, we will generate just a vector for all possible actions. So we will have the Z, but tau will be given on the input, not on the output. So this is going to be computed by processing the state in the same way as before, so some convolutions and the fully connected layers. And then we need to also include the tau on the input, right? Because we need to be parameterized by the tau. So how to do that? there are definitely many possibilities how the result of the state and the result of the tau, or the embeddings of those, can be compared. The authors consider some number of them, but in the end, the element-wise multiplication worked the best. So they say that this forces the largest interaction between the state representation and the tau embedding. They represent the quantile by an embedding with size 64, and it's being computed by considering the cosine embedding of the tau, but trainable one, right? So how you can look at this and saying, okay, so we have a fixed cosine embedding for a given tau, right, such that it is cosine of pi times 0 times tau, cosine of pi times 1 times tau, cosine of pi times 2 times tau, and so on. Right? So it's like a periodic kind of vector. And then we pass it through a single hidden layer with ReLU activation. They also consider the case where instead of these cosine embeddings, they would just use learnable embeddings, and it works, but slightly worse than this one, right? Yep. So, how does the loss look like this time? Well, the only difference is that previously we just considered n taus for the distribution being trained, and n taus for the distribution which is the result of this Bellman update. Here, instead, we just generate them uniformly randomly from the interval 0, 1. And we generate n quantiles for the distribution being trained, and then n prime quantiles for the distribution which we estimate. So that's the result of the Bellman update. That's what we want to get close to. They use the same values in the end for both of them, but they have a large discussion showing what the effect of those are. And generally, the idea is that the n is the number of the quantiles which we train. So more of them we train, the faster or so we train. So it makes sense to have this quantity large, because if we train just a single one, we would train just one value out of these n's what we did before. So this needs to be reasonably large. On the other hand, when we try to represent the result of the Bellman update, the thing which we try to get to our target, then from them, sampling just a single quantile still gets reasonable results, but, well, in the end, increasing both of them makes sense, and they actually use 8 and 8. But the good thing is that the n is now not like like an architecture choice of the network. It's just the question of how many samples from the distribution we will generate, because we have this probability, so we can explicitly generate as many samples from the distribution as we want. Yep, and that's it, right? Because then we have just the final evaluation, which shows, okay, compared to the QRDQN, we are still better. They come, and of course, compared to C51. They also compare to full rainbow, but this IQN is just this, right? So no n-step updates, no other of the improvements, just this one. So it's still worse than rainbow. And unfortunately, I haven't really seen any evaluation where you would take IQN and then use the full, like add all the improvements which rainbow has. But it could be done easily. Yeah, and then they just have some ablation experiments showing that combining the embeddings for the tau and for the state, it's better to do the multiplication instead of the concatenation. Sigmoid or relo activation, I don't know, I would say not a large difference. Embedding size, again, not very large difference, but the cosine embeddings on the input is definitely better than the learned ones. So I hope you like the new lecture. If you think it was a bit too dense on the math, don't worry. I don't want to punish you for that on the exam. The idea is to understand even the difficult stuff. So don't worry about it. And I will think up an assignment where we will be able to actually implement it, because I think that right now it seems very abstract in your minds. So we will implement it, and that hopefully will show you that in the end it's not difficult. It's just we needed a lot of theory to know why these 5 lines which are there will work. Thank you very much for your attention. I look forward to the Wednesday's practicals. We'll have the award ceremony for, don't we? Is the lunar lander ending already or not? Yep, is it? Yeah, thank you. So we will have the award ceremony for the lunar lander, so I hope it's landing nicely for you. So see you on Wednesday.